Good morning, and thank you guys for coming. Good morning. In the next hour, I'll be talking about parallel link or PLINQ. I'll talk about what it is, how does it work, and how you can use it to optimize your program so that they run faster on multi-core architectures. PLINQ is one of the number of new components in Visual Studio 2010 that target parallel computing. We've had a number of parallel computing sessions on this year's PDC. I have a list on the slide right here. I won't go through the slide in detail, but my slides are online, or will be online, and all of the videos will be posted on channel9.msdn.com. So definitely check out the sessions that you haven't seen to learn more about parallel computing in a broader context. We have a lot of interesting material to get over, so I will only do a quick introduction, and we'll move straight to looking at some PLINQ coding examples of the types of patterns that PLINQ fits very well, and how you can use, and how PLINQ executes those particular, how it behaves on executing the different types of queries. And then I will look at the most common pitfalls and tips for parallel computing, and specifically for using PLINQ, but also in general when writing code for multi-core. What are the kinds of things that you have to look out for? This is a 400-level talk, so there are some prerequisites. I will assume understanding of .NET, C#, and basics of LINQ and threading. I have a couple of quotes here to illustrate a few points about multi-core and .NET Framework 4. We got this feedback from Carl Caddy, who does biology research at a Microsoft research group, and they started using Task Parallel Library and PLINQ to do some of this in parallel, and they found that now the computation takes 10 minutes, where previously it used to take an hour, and that has a big impact on how they can do their work. Now, it completely changes the workflow. And so once you start getting to 4, 8, 16 cores, writing your code so that it takes advantage of the multi-core architecture has a huge impact on the performance. Now, most of the desktops and laptops that you can buy in stores are dual-core or quad-cores. And if you buy a dual-socket motherboard and you put 2 quad-core CPUs into it, you have an 8-core machine. And so the hardware is already available. It's about figuring out how to best take advantage of it in your applications. MS Build is another group at Microsoft that has adopted our early bits, and they found that with the new .NET 4 improvements to parallel computing, parallelism is more practical and cost-effective to implement, where it would have been hard to justify the cost of doing all of the threading and synchronization and all of the hard work to make parallelism work themselves. And finally, one other quote that I'll point out is from an independent IT consultant and author who, the point of this quote is that I want to show that there's a lot of excitement and interest in the developer community about multi-core programming. Developers want to know how they can use the multi-core architectures to deliver new user experiences and make their programs faster and do more exciting stuff. And in Visual Studio 2010, there are a number of new components and tools that make it easier and more more practical to take advantage of multi-core in your hardware. On the tool side, there's a new debugger tool and a new concurrency visualizer. For programming models on the managed side, we have parallel LINQ and a task parallel library. And on the native side, we have a parallel patterns library and an agents library. And there have been improvements to runtimes both on the managed and the native side. And Windows 7 introduces some improvements to concurrency as well, the UMS threads. And the component that I'm talking about today is parallel LINQ. That's one of the managed parallel programming models. At the API level, PLINQ is very similar to LINQ to objects. We try to make the API and the behavior to match as closely as possible. So I will show a simple LINQ to objects query. I have an array, and I apply a single select operator to it. And then I have a toArray operator. And what that does is this query will iterate over the array, and it will evaluate the foo function for every element in the array. And then it will collect the results into an output array. And so if the foo function is expensive, you can take advantage of parallelism by running different invocations of the foo function on different threads. And to do that, you can simply add as parallel after the input data source. And by doing that, you wrap the input array with a parallel query wrapper, and all of the operators that are chained afterwards will bind to PLINQ implementations, to the PLINQ overloads rather than to the LINQ to objects overloads. I will show this example in more detail in Visual Studio. The example that I showed is you have an array and you want to do an expensive operation for every element in the array. It's kind of the simplest query that I'll show today. And first, I'll show the sequential implementation that is very simple. I'll just use a for loop. I have some pre-written benchmarking code here so that I don't have to write all the stopwatch code. So what I'll do is I have an array of integers, and I want to evaluate some expensive function for each one. And the function that I'll do is I'll check whether each number is or isn't a prime. I'll create an array of bools results equals new bool, and it will be the same length as my input. And now I'll use a for loop to iterate over the input array. And I'll compute the results one by one. OK, that's better. And this is the simple sequential implementation. To convert it to LINQ to objects, I will simply use a single select operator, kind of like the way I showed on the slide. I'll just say array.select, x goes to utils.isPrime, x.toArray. And I'll also convert this query to PLINQ. And to do that, I only have to add as parallel. So I'll add as parallel here after array. And now I can see in IntelliSense that the select overload that is being bound to is the one that operates on parallel query versus this select operates on IEnumerable. So it's a completely different method. I'll run this without the debugger attached. And the sequential code, the sequential version of the algorithm is using the for loop. That takes 360 milliseconds. The LINQ version takes about the same, also 360 milliseconds. And the parallel LINQ version, it takes about 92 milliseconds. This is a quad-core machine, so it is using 4 cores in parallel to evaluate the is-prime methods. And that's where it gets the speed up from. One other thing that I'll show is I'll put a breakpoint into the is-prime method. By the way, are there any questions about this so far? No questions. I will put a breakpoint into the is-prime method. I already have it there. And now I'll run with the debugger attached, except that I'll only run the parallel version. And I want to show the new parallel stacks window that's new in Visual Studio 2010. The parallel stacks window shows you the stacks of all the threads that are running at this moment. And right now there are 4 threads that are executing the is-prime method. 3 of them have this shorter call stack, and those 3 are the worker threads that PLINQ is using to offload some of the work of evaluating the is-prime method. And actually PLINQ doesn't use threads directly, it uses the task parallel library, and the task parallel library uses a thread pool, and the thread pool itself directly is manipulating the threads. And there's one thread with this longer call stack. And this is the thread that is running your program. That is the thread that has program.main at the bottom. So PLINQ reuses the main thread to participate as one of the workers in this particular query. Now I'll switch back to the slides, and I'll show a diagram of what happens when this query executes. This is the simplest case that I'll show today, because the input and the output of the operation are arrays. And arrays are a good data structure in the sense that you can read and write to different locations without contention. So, for example, in PLINQ, if you want to compute results 0 through 9 in the output array, one thread can do that computation. If another thread is computing results 10 through 19, they don't interfere. There is no contention either on the input or the output data structure. And so long as they agree on which thread is processing which elements, there's going to be little overhead, no synchronization needed or anything like that. One other thing that I'll point out in this example is that PLINQ partitions the input array statically by default. The default is that if you have 4 threads, or on a quad-core machine, PLINQ will use 4 threads, and the first thread will process the first quarter of the array, and the second thread will process the second quarter of the array, and so forth. I will show you later how you can change this behavior and use either a load balancing partitioning scheme or your own partitioning scheme that you have implemented yourself that fits your particular data structure or your particular workload. So the first example that I showed used an array as an input and an, oh, sorry, yeah.
So is it taking into account that the enumerable you're passing to it is like an I collection to get the length to do the partitioning then?
It does PLINQ currently does special things. Oh, sorry. The question was whether PLINQ does checks whether the input sequence is a collection, and whether it uses the length property to determine the length. And the answer is that PLINQ does special things for arrays and I-lists in the current implementation. Right, because with a collection, with arrays or I-lists, you can get the length quickly, and you can also get any particular element in a constant time, or at least that's the assumption behind the interface. With a collection, you don't have that fast indexer. So even though you can't get the length, you can't get the other part of it. A slightly more complicated example is when the input is not in an array, but instead it's a general IEnumerable. PLINQ, like LINQ to objects, works with any IEnumerable, so it can be a sequence generated by LINQ to objects. It can be a sequence of results from a SQL database or sequence of data that is read from a file. So long as it implements the IEnumerable interface, you can apply the asParallel method to it and follow up with PLINQ operators. And in that case, PLINQ can't conveniently just read different parts of inputs from different parts of the array, because there's no way to jump into the middle of an IEnumerable, to jump the enumerator halfway through. So what PLINQ does is it uses a lock to protect the input enumerator, and different threads are pulling input elements from the enumerator. So if you have 4 threads, whenever one thread is ready to process more elements, it will take the lock and it will remove an element from the input enumerator. Our default partitioning, actually, the thread will take 1 element the first time, and eventually it will start taking 2 elements and 4 elements, and gradually it will take larger chunks from the enumerator each time to amortize the cost of taking the lock. And so each thread is computing the result, pulling the input elements from the enumerator, computing them, and placing results into its own buffer. And at the end of this stage, you have as many buffers as you had threads, and each one has results generated by that thread. And in the second phase, these buffers are combined into the output array, and the output array is returned to the user. One other thing that I'll show here is the problem that comes up with order. When you think about it, when the threads are pulling input elements from the input enumerator, as they do that, you lose the information about the relative input ordering, how the elements were originally ordered in the enumerator. So if thread 1 pulled 5 from the input enumerator and thread 2 pulled a 7, after you've removed the elements, you've lost the information whether the 5 came first or the 7 came first, unless you somehow explicitly persist that information. And by default, PLINQ treats an input sequence as an unordered sequence. So unless you explicitly say input.asParallel.asOrdered, as I'll show in 2 slides, PLINQ will assume that you don't care about the relative ordering of elements in the input sequence. And so when putting the elements together from different buffers, it just puts them together. It doesn't try to reestablish the original order. The 2 examples that I have shown so far were both synchronous queries. So when you set toArray, before that method returned, the entire query has already executed. PLINQ can also execute these asynchronous queries where the results are getting computed by n threads. And as they are getting computed, each thread places the results into its own result buffer. And at the same time, the for each loop is driving the output enumerator that is pulling the results from the different result buffers. And so in terms of the query, the difference in the query is that instead of ending with a 2 array, you use a for each loop to iterate over elements of the query. And PLINQ will create these workers, and the workers will be generating the results, and the for each loop will be driving this output enumerator that will be pulling results from the buffers as the results are getting generated. When you put as ordered, oh, do you have a question?
When you're doing the asynchronous processing that way with for each loop and iterating through it, is there locking on the back end too to get the sequence out?
So the question was whether the merging phase uses locking as well, right? Our algorithms try to minimize locking, at least if none of the result buffers contains anything, the main thread has to go to sleep. And so it has to block, and then so there's some blocking and there's some synchronization there. But in the best case, the algorithms are designed so that they try to limit the amount of blocking. For example, actually, we don't pass in the results one by one, but they get passed in chunks of some size, 128, depending on I think it also depends on the size of the data type. And that goes a long way towards eliminating the blocking and the cost of locking and synchronization. If you want PLINQ to persist order throughout your query, you can put as ordered on the input data source. And PLINQ, when it pulls elements from the input enumerator, it will remember their original positions in the input sequence. And then it will track those position indices throughout the query, and then use an reordering buffer to reestablish the correct ordering of the output elements. And PLINQ can do this even for asynchronous queries. So not only for all of the results won't be materialized and then sorted by position and then yielded. PLINQ actually, as the results are getting computed, it uses this temporary buffer to reorder the results. And once it knows that it can yield certain results, it starts yielding them to the consumer loop. And that is a very useful feature, because you get ordering, but you don't have to materialize all of the results into an array or another data structure. Another example that is often useful for parallel processing is aggregation. You have a sequence of elements, and you have a function that combines two of those elements together, and you want to combine it together to a single value. LINQ to objects has a number of aggregate overloads. PLINQ implements all of those, and we also add a couple more that are specifically well suited for parallelism. There are some subtle details that deal with specifically the accumulator value and how there has to be more than one instance of the accumulator value. There are some details why we have to use, why the PLINQ specific overloads can be best for certain situations, specifically when the value that you're accumulating is a reference type. I won't go into it in detail, but we have a post on our blog that explains this in detail. I will show the link to the blog on the last slide. But in an aggregation, at the basic level, you have a sequence and you want to combine it to a single value. And in parallel, you can have multiple threads, each one combining a partition of the input to a single value. And then each thread produces a local result in the first phase. And then in the second phase of computation, all of the local results are combined into the final result that is returned to the caller of the query. Another example that is sometimes useful is search. Search is when you have a where operator followed by a first operator. And PLINQ will, in this case, find the first element in the sequence that matches the predicate. And it will use multiple threads to evaluate the is prime predicate. And it will handle all the messaging between threads that is necessary to make this happen, to execute this type of a query. I'll also show an example of how PLINQ executes a more complex query. PLINQ can execute any link to objects query. And I have an example here of a query that contains a filter, group by operator, and that groups the numbers that haven't been filtered out into groups that based on the modulo 5 values of the integers. And then we process each group. So from each group, we'll pass it into this process group function that is user's function, and they will return the value that they want for that particular group. And this kind of query executes in 3 phases. In the first phase, PLINQ filters out each sequence and also shuffles the values so that values that are together in one group will be in a single buffer. In the second phase, the groups themselves are projected. So for each group, we will evaluate the process group user function. And this part is also happening on multiple threads. And finally, in the last phase of the computation, the buffers that were produced by different threads are all put together into the final result array. And so regardless of whether it was this phase that was expensive or whether this phase was the expensive part, you should see parallel speedup because PLINQ uses multiple threads to evaluate both parts of the computation. And if they both contribute about equally, then you should still see scaling. I'll talk about the most common performance issues that people run into and the most common ways of fixing them. These are both for multi-core programming in general and issues specific to PLINQ. It's kind of strange that for multi-core programming, there are some of these issues that you never run into or rarely run into when writing sequential programs, performance issues, but you run into all the time when you're writing multi-core programs. And it is important to have a set of tricks in your toolbox so that you know how to identify those issues and how to fix them. The first common issue that people run into, this is when somebody wrote a parallel code, a multi-core application, and it is not scaling. One of the common reasons why it is not scaling has to do with memory allocations. It's easy to write code where the memory allocations and GC are by far the dominating factor in the execution. If you write something that is concatenating strings or doing a lot of boxing, or if you just represent your data as a lot of small objects, it is it's easy. It's easy. It's quite possible that GC and memory allocations will take 80–90% of your execution time, and then it doesn't matter how well the 10–20% of your the remaining part of your program scales. Your program will only scale in practice as well as the garbage collector scales and as the memory allocations scale. And by default, the default .NET garbage collector is called the concurrent GC. And it is highly optimized and fast, but it's highly optimized to lower the latency. Its main purpose is, or the main scenario that they had in mind is when you have these applications that are interacting with the user and you don't want the user interface to hang. So you want to minimize the latency. If you have on the other hand, you don't necessarily it's not necessarily optimized for running getting the maximum possible throughput on multi-core machines. There is a GC that is optimized for that, and that is the server GC. And I will show you what kind of impact this the garbage collection and memory allocations can have. I have an example pre-written here. I will just change the main method to call my example. It's memalloc.go sequentially. And I will change the label that shows up on console so that we can understand what is happening. And I will also call the parallel version of my code. And now let's take a look at the example itself. I have a very simple link to objects query here. This is the sequential example. I have a sequence of 10 million integers, and for every integer, I create an instance of an anonymous type. And in C#, anonymous types are implemented using heap allocated objects, at least in the current version of C#. So this example will be actually creating, allocating a new heap allocated object for every input element in the sequence. So it will be allocating 10 million heap allocated objects. And I have a parallel version of the same code sample. I just changed enumerable to parallel enumerable. And let's try to run this. Now, in the past, when I tried this, the performance of the parallel version varies a lot. But I got a good example. I got a good running time. The running time varies between 120 milliseconds and 290 milliseconds for the parallel version. But I got the example that demonstrates the point that I was trying to make, which is that the algorithm, in the worst case, is quite slow, and its performance seems to go up and down. And the non-determinism comes from the GC, because the running time of the GC seems to vary a lot from one instance to the other. But usually you don't get a very good speed up. And in the worst case, you don't get any speed up. One possible fix is to reduce memory allocations in your program. And that way, you don't have the problem with GCs and memory allocations at all. The way I'll demonstrate this is that I'll use a value type instead of the anonymous type. I'll use a value type that contains a single public int value field, and then I'll change this anonymous type to be the value type instead. And so reference types, if it was a class, every instance is allocated on the heap. If it's a struct, it's a value type, and it is allocated kind of in line wherever it is referenced. Well, so if you have a value type as a local variable, it will be allocated on the field, on the stack. If you have a value type that is a field on a heap allocated object, the value type will be allocated on the heap, obviously. And so in this case, the wrappers will be allocated on the stack. And we should see much better scaling. So both of the algorithms were faster now because you're not doing memory allocations. But also the parallel algorithm was much faster, and also it scales well. You get about a 3 times speed up compared to the sequential algorithm after we fixed this problem with memory allocations. Another possible way to mitigate the problem with memory allocations is to turn on server GC. So I will go back to the version of the code that does a lot of memory allocations, that does not use this struct. And the way to turn on server GC is to add an app.config file to your project. To do that, you just have to go right-click on your project and say add item and find the app.config in the list of things that you can add. And you can add this runtime GC server enabled tag. And this will turn on server GC for the application. The server GC has to be turned on for the entire application because it changes the way .NET allocates memory. In server GC, there is one heap for every core. And so when the GC runs, the heap can be collected in parallel because different threads you can have, on a quad-core machine, you can have 4 threads collecting 4 heaps independently. And so this algorithm scales quite very well on multi-core machines. And let's try to run this. And we should see that the parallel algorithm will run about 3 times faster than the sequential algorithm, even more actually, 3.5. And this result seems to be stable. If I run it many times, it will always be 3.5 times faster in the parallel algorithm compared to the sequential algorithm. And so this demonstrates that memory allocations are an important thing to watch when you're trying to optimize your program so that they scale on multi-core. Another similar issue to memory allocation that also often trips people up has to do with the way CPUs exploit locality, the way caches work. On a multi-core architecture, usually, or on the x86 and x64 architectures, every core has its own cache. And when one core modifies a particular value in memory, that value in memory has to be invalidated in all of the caches. The other cores can't use their own copy, their own cached copy of that value anymore. But actually, the other part of the problem is that caches don't work at the granularity of bytes. They work at the granularity of cache lines that are 64 or 128 bytes on today's CPUs. And so when a value is invalidated in the caches, actually the entire cache line is invalidated. I have a diagram here that shows what happens. I have values 5732 in main memory and 4 cores. Each one has these values in its cache. And you can think about, for example, the case where core 1 is reading and updating the first value, the 5, and core 2 is reading and updating the second value, and so forth. And what happens is that thread 1 wants to update the value 5. So it overwrites the value in its own cache with the 5 with a 6. But now the entire cache line for cores 2 through 4 will be invalidated. And now if core 2 wants to update value 7, its own value in the cache, then it will again invalidate everybody's cache. And what happens is that most of the memory accesses end up going to the main memory, or at least to higher cache levels, the ones that are more expensive to access, instead of to the fast caches. And this may seem like a weird, obscure thing, but actually it has it is one of the top issues that come up, at least that we've seen most often from people that try to write scaling parallel multi-core programs. I have an example here that I'll show just how much of an impact this can have. I have a simple sequential example here that I'm computing. I have an array of size 4, and for each of those elements, I am going to iterate 10 million times and update the value in that particular array location. If this example seems kind of naturally parallel because you can update different counters on different threads. So you can implement the parallel algorithm either with a parallel loop or with a simple PLINQ query. I used a simple PLINQ query that is just parallel enumerable.range.forAll. ForAll is a new operator that we added in PLINQ that wasn't in LINQ to objects. But the interesting point is that now the inner for loop will be done on multiple threads. So thread 1 will be updating count 0, and thread 2 will be updating count 1, and so forth. And so what we would expect is that the parallel version should be 4 times faster than the sequential version. But actually, we find that it is almost 10 times slower. So it's a difference of a factor of 40 in the expectation of performance because of this weird false sharing problem. So we want to fix it. One possible way to fix it is to pad all of the values. So when you are updating a particular counter, you are not invalidating the counter of another thread. I have a fixed version of the code here. I use a padding of 16 integers, so padding of 64 bytes. And when accessing a particular value, instead of using locations 0, 1, 2, 3, I use locations 16, 32, 48, and 64, so that every element is padded both from left and from right. One interesting thing is that you can't use values 0, 16, 32, 48. The first element has to be padded from the left, and that is because .NET stores the array length just before the first element in the array. And so if you don't pad, if one thread keeps updating element 0, it will keep invalidating the cache line that contains the array length. And so all of the other threads that are trying to do range checks will have to keep getting that getting that array length from the main memory. So I have the fix here that works properly by padding both from left and right, and I'll run that now. And now we find that the parallel algorithm scales roughly as expected, takes 17 milliseconds. So we get something like 3.5 or whatever it comes out to. We get some good scaling roughly compared to what we would expect on a quad-core machine. So this is one possible fix, is to make sure that, that the frequently updated locations in memory are properly padded. It may seem like a waste of memory, but given the dramatic performance impact that fault sharing has, it is well worth it to waste some dozens of bytes for the padding. Another possible fix that I'll show takes advantage of the fact that memory allocated by different threads tends to stay apart. It's definitely true on the server GC. It is even more true because there are multiple heaps and different cores are using different heaps. So there it is either guaranteed or almost guaranteed that that if you allocate some memory on one thread and you allocate another memory on another thread concurrently, that the memory allocations will be apart in memory. But it seems to be the case even on the default GC, that if a thread allocates a particular location in memory, it is safe for that thread usually to update that location without running into these fault sharing issues. So the way I fixed the problem here was that I used instead of using an array of integers, I use an array of arrays of integers. And the first thing each worker does is it allocates an array of length 1 so that it is mutating its own, so that it is mutating and reading the value it allocated it itself. And when I run this code, now it takes 20 milliseconds in the parallel case. Before it was 18 milliseconds, maybe it's just a little bit slower because we're doing 2 levels of memory accesses here, 2 levels of array accesses, but it is still much, much faster than the version of the code that was getting fault sharing.
Would this only work if you do the allocation on separate threads for the internal array?
So the question is whether this only works when you do the
Like right now you're doing the second dimensions allocation inside each thread. Does it work if you have it separate? They are separate references.
Right, so the question was whether it is important that the different arrays of length 1 are allocated on different threads. And it actually is important. If all of these values were allocated on outside of the parallel for loop, so it would be allocated on the main thread, they could still be close in memory because they would all go, I mean, the allocator is likely to put them one after another when you allocate them on one thread. And the overhead of arrays, I don't think is big enough to, or is not big enough to push you into the next cache line. So you really want to you want to ensure that 64 bytes or 100 or maybe 128 bytes, depending on the architecture, from the value that you are writing. There's no other value that you're also frequently updating on another core. And I don't think that allocating different arrays will be sufficient. That would not probably work. I am going back to my slides. And actually, fault sharing is one of the, yes, another question?
Yeah, does that only work if you have server GC since these ones getting?
The question is whether the fix that I showed, the one that allocates the small arrays, only works on server GC. And in practice, it seems to work on both server GC and concurrent GC from my experience. I don't believe there's any fixed guarantee because the garbage collector is free to compact stuff and shuffle. It doesn't make any explicit guarantees, but in practice, it seems to work. At least work often.
Determining the cache line size, you just have to define that up front and compile for particular architecture, or
Yeah, the question is whether there's any way to do this without depending on some hardware details. And there isn't really anything that you can do there isn't really a way programmatic way to figure out the cache size. That is, you kind of have to write the code that depends on some hardware details, unstated hardware details. That's the way kind of always with caches, is that caches are in a way transparent, but when it comes to performance, they are not. And then you have to write code that is tweaked towards particular cache implementations. And if in the future there was a completely different architecture with completely different caching, your optimizations might actually make things worse instead of better. But in this particular case, this issue shows up on all of the x86, x64, all of the mainstream CPUs. So you're pretty safe if you fix it. It's quite likely that the CPUs that are coming out anytime soon are going to behave similarly. At least that would be my expectation.
In this case where you assume 64,
Mm-hmm.
if you assume 128 was a good thing, so you'd have 2 lines would be validated. But what would be attached to that?
The question was whether it would be safe to assume 128-byte cache lines rather than 64, whether it would still fix the problem if the cache line size is 64. And yes, it would fix the problem, so long as you can always assume larger cache line sizes. You can't assume a smaller one. So I could make the padding much, much larger. I could make it 10 times, 100 times larger. I will just waste more memory. That is the only downside. And one interesting thing about fault sharing is that, in my view, it is one of the less obvious reasons why automatic parallelism is hard. Often people ask, why can't just the runtime do all of the parallelism stuff underneath automatically? And there are many reasons why. There are many difficulties with correctness. But then there's also reasons like fault sharing, that sometimes doing stuff in parallel is actually a lot slower than doing it in sequentially. So that adds kind of this another axis of difficulty to that type of a problem. The best way to use PLINQ is to use computationally expensive delegates in simple queries. The examples that I showed so far, or the examples that I showed in this presentation, were generally simple queries with 1 or 2 operators that used an expensive delegate. And that is because that's how PLINQ is used most effectively. You may sometimes be able to use a cheap delegate over a long sequence, but the problem there is that the PLINQ API introduces some necessary overheads. For example, there's when you pass in delegates into your operators, and calling those delegates invokes a virtual method call. And working with enumerators also requires virtual method calls. So you might get into the situation, if all that you're doing for each element, the actual work is a couple of additions, then the virtual method calls are going to dominate your running time, and you'd be better off writing a tight sequential loop as opposed to writing this parallel algorithm that is parallel, but it's doing all this extra virtual method calls. Another good tip for writing PLINQ queries is to write the simplest query that you can get away with. Don't write a complicated query if you don't have to. And even though PLINQ can execute any link to objects query, I have an example here of a query that contains a select, take while, and a select. And I put the S parallel after the take while so that the first select and the take while execute in link to objects. And when you run something in link to objects, it has usually fairly simple semantics. If you think about how take while is implemented, then you'll quickly figure out how it is implemented and what are the performance characteristics of that implementation. And then the PLINQ part of the query is also simple. You have an IEnumerable, and you use a single select operator on it. So you have two simple pieces instead of having one complex piece where PLINQ is handling stuff under the covers. For somebody that is familiar with PLINQ and that is at least a little bit, and that is going to read this query, they will have a pretty good idea of how this is going to behave performance-wise. Partitioning is also an important factor in parallel algorithms. Different partitioning algorithms differ in overhead, in their load balancing properties, and in the required input representation. For example, the default partitioning on arrays that I showed that partitions arrays statically has no load balancing, it has low overhead, and its input must be an array. You can change the partitioning scheme that PLINQ uses by using the partitioner type. .NET 4 ships with a few different partitioning implementations, including a load-balanced partitioning for arrays. And you can also implement your own partitioning algorithms by deriving a class from partitioner and implementing the virtual methods. Finally, PLINQ is like any other optimization, and you should think about it the same way. So measure your code before, understand the slow parts of your algorithm, and if the bottleneck fits the pattern of a PLINQ query, then try to use PLINQ to split up that work to execute in parallel. And make sure to measure again and validate that the code is now faster, so that you know that you've actually made the code faster, not just more complicated. And if you don't see an improvement, then the 5 tips that I mentioned are the most common reasons why you would not see an improvement when you expect one. And also, you can check out some of the new Visual Studio tools. The parallel concurrency visualizer is useful for figuring out the problems where the threads are blocking or there's some sort of synchronization issue. More information about these topics is up on our concurrency on our parallel computing dev center. We have some code samples. We have an active team blog, and the tools team have their own team blog. We have active forums, and I also put up my blog, my personal blog up there. Your feedback is very important. We use it to decide what kinds of content we should be doing in the future, what types of sessions should be done. So please go up at microsoftpdc.com and fill out the session evaluation.